Hello everyone and welcome to another episode of YouTube live training with Man and Machine. I'm your host Francisco Perez Smith, and today we're going to continue our series on learning Fusion 360 during this COVID pandemic. So today we're going to be focusing not on designing things so much as analyzing designs that have already been created. So let's just jump into it. Hopefully you can see my screen all right. Looks good. Okay, so what we have here is a very simple design. It's going to be a very small clip. This clip is going to be loaded in a very simple way. This foot here is going to be fixed to the floor, and this foot here is initially going to be fixed to the floor. It's then going to be loaded with a small force that will act down uniformly on the surface. And we're going to see how this shape resists the load. We're then going to put another load case on where this foot is fixed, and this one is allowed to slide in the X direction. So let's just get started. To begin, we'll leave the design environment for the first time. We'll say design, and then we'll come down to simulation. What Fusion allows us to do is not only create the geometry for our models, but also to analyze the performance. So here we'll come to simulation, and here we have many different tools. We could start by simplifying the geometry, but we're going to skip over that for this demonstration. Here we have linear static stress, which is the first one that we're going to be having a look at. In this study, the load is going to be applied slowly and uniformly, and we're going to see how it affects the structure. We have some other studies which we'll visit later, such as modal frequency, so this is how the thing vibrates, electronics cooling, thermal, structural buckling, nonlinear static, a whole plethora of them. We'll start off with static stress. So let's go ahead and click Create Study. Lovely. Here we've got it's basically finite element analysis. So what we're going to be doing is prescribing to the machine what is the load case for this particular design. That is to say, how is it going to be constrained, what loads are going to be applied, what material is the part made out of. And then we're going to have the machine break it down into lots of little parts, and it's going to tell us what the stress is in the component. So let's go ahead and start off by prescribing the material. So here we can say materials, study material. Fusion comes with a whole wide plethora of different materials, complete with material data. And we can choose any one of these. We could choose stainless steel, or we could choose aluminium. For this exercise, what we're going to do is choose steel-mild. There we go. Lovely. If the component had a material already, say it was mild steel from the design perspective, it would be brought over into the simulation, but no material was assigned, therefore it was left as generic, and we have to override it with a valid material. What we have here in the final column is the safety factor. So when it's calculating the safety factor, i.e. how strong the design is relative to this, are we deciding whether it's relative to the yield strength of the material or the ultimate tensile strength? For this exercise, we'll choose yield strength of the material, and we'll explain what that is a little bit later. We'll say OK. Next, let's go ahead and prescribe some constraints. So we'll say constraints, and here we've got structural constraints. These structural constraints are prescribed relative to the environment. So here we have a couple of types. We've got fixed, pin, frictionless, prescribed displacement. Let's go ahead and choose fixed, and we're going to pick this face here. It would be possible for us to select both of these faces, but just for the sake of this exercise, we're going to do it twice. So we'll say fixed and click OK. And what we have here now under study 1, we can see our study materials, mild steel, and our load case. So if we expand that out, we can see the loads and constraints that make up this load case. We'll expand both of those out. And under constraints, we can see fixed 1. Here, if we wanted to, we could rename it. We might say fixed 1, left leg fixed. We might go ahead and make another constraint, selecting the right foot, and keep that fixed in X, Y, and Z as well. And we might rename that one fixed 2, right leg fixed. Next, what we might do is prescribe our load. So we're going to specify a load, and it's just going to be a uniformly distributed force that acts downwards on this surface. These blue arrows are just glyphs that are indicative of the direction that the force is going. If we wanted to, we could change the direction using these dials, but for now, it's just going to be acting directly downwards. So we're going to say a magnitude, and it's going to be 16 newtons acting down on that face. Wonderful. Okay, so what we've got for load case 1 is we've got a load acting down, 16 newtons. 16 newtons. We've got the left leg fixed and the right leg fixed. The only thing that's left to do is to create what's called a mesh. In order for Fusion to calculate the stresses in the component, what it needs to do first is to break down the component into lots of little parts. These are tetrahedral in shape, but we'll have a look at that now. So here we can see mesh, and we can right click, and before we do anything, we're going to click mesh settings. Here what we have is the default mesh settings for how fine this mesh is going to be. I prefer to use absolute sizes, in which case we tell Fusion what size elements we are going to use. We're going to start off with a relatively coarse mesh. We'll say 4 millimeters and click OK. And then we're going to generate the mesh and see what it looks like. Generate the mesh. And you take a little bit. And there we go. For a first pass, that might be acceptable, but for more accurate results, we might make this mesh a little bit finer. So to do that, what we'll do is right-click the mesh here, Mesh Settings, and we're going to change the absolute size to 1.25. The finer the mesh is, the longer it takes to calculate, but the better the results will be. So there we go. The mesh is a bit finer, and it's what you're looking for is that the mesh better represents the shape that you're trying to simulate. Okay, so let's review. We have our material, which is mild steel. We have prescribed our load case, which has a 16 Newton load acting down on the top and has fixed the left leg and the right leg. Let's go ahead and go to the solver. Now, because Fusion 360 is cloud-based, we can elect to choose either to solve it locally or on the cloud. Because this is a small problem, I might just choose to do it locally, and we'll see how that goes. And click Solve. And Fusion is now doing the calculations on those finer elements, and it's done. Very simple case. So what we can see here by default is a heat map that shows the safety factor of the material. But in order to understand what that means first, we first have to look at the stress. Let's go and change the criteria that we're looking at, the metric that we're looking at from safety factor to stress. Lovely. Okay, so what are we looking at here? What we see is a nice rainbow chart. We see colors that gradate from blue to red. What does it mean? What we can see is a little legend at the bottom right-hand corner, showing the minimum stress experienced in the component and the maximum stress. Now, the yield strength of mild steel happens to be around 207 megapascals. The yield stress is the stress that's required in order for the material to experience plastic deformation. That is to say, once it goes beyond that stress, it will change shape and never return back to its original shape. Now, what we can see here is that we've got a peak stress of 104 megapascals, which is about half of the 207 megapascal yield strength limit that I was just talking about. Now, we can see that when we change the stress to safety factor, that we can see that the minimum safety factor is about 2. That means that relative to the yield strength, the material is experiencing only half the stress that it requires to plastically deform. So if that was your only criteria, you could say that it's twice as strong as it needs to be. Now, I'll show you something very, very cool about the legend. This isn't just a static graph. What you can do is you can drag up the minimum and maximum, and you can limit the amount of material, the range of stress that you're seeing. So it may be that you're only interested in the areas that are experiencing 44 megapascals or higher of stress. This might be if you have to consider the fatigue life of the clip. So there we can see all the volumes, all the volume that's been subjected to that level of stress. If we bring up the legend, there we can see we are only focusing on everything that's got 88 megapascals of stress and higher, which is pretty much isolated to near where the platform where the load is being received. Pretty cool, pretty cool. So lastly, we might be interested in seeing, how much does this actually deform? We can see that, from our graphical window, it looks quite squashed, but is that actually what's happening in reality? We'll change the metric from stress to displacement. And here we can see the actual displacement value, the peak displacement value of the clip. And we can see that the peak displacement is only 0.01663 millimeters, so barely anything. So, why is it showing this big exaggerated example, big exaggerated clip? Here we can change how the clip is being how the deformation is being expressed. By default, it shows quite an exaggerated deformation, so we can visualize how this thing is deforming. This can give us hints for how we can strengthen it. But if we want to see the true deformation, all we need to do is come up to this button here. And there we can see the true deformation of the model. It's barely noticeable to the eye. Lovely, very easy, but also a very simple example. Let's go on and look at some more complicated examples. So in this next one, we have a very fancy lever. And what it's going to do is rotate about an infinitely stiff pin, which we're going to fix in space there. Someone's thumb is going to press down on this surface with, say, maybe 200 newtons. And this surface here is going to be able to slide in plane, but not move up and down. So let's have a look at how we could calculate that. We're going to leave the design environment, and we're going to go over to the simulation tab. And once again, we'll go over to static stress. To repeat what I was saying earlier, static stress analysis, loads are being applied slowly and consistently. The stress tends to be well below the yield stress, and it tends to not deform that much. So let's go ahead and say create study. Now, as before, the first thing that we're going to do is we're going to define the material that makes up this component. So this time, by default, the component has been defined as mild steel, but we may wish to see, what would it be like if it was simulated as aluminium 6063? So let's go ahead down to aluminium, 6061. So we go aluminium 6061, click OK. And what we're doing is overriding the mild steel that's been given to this design. And we'll say OK. Next, what we're going to do is apply some constraints. So the first constraint that we're going to apply is a structural constraint, but it's going to be slightly different before. So we're going to specify a pin joint here. And what this pin allows us to do is select a circular surface, and we can prescribe how it's being fixed in space. Is it allowed to rotate? Is it allowed to translate along the axis? Is it allowed to move axially, radially, tangentially? Here we can choose what we're fixing. So by default, we're fixing the axial movement, which is along the circle, along the axis. Next, we've got the radial, which is moving it from side to side, up and down, and tangential, which is the rotation. Now, we want it to rotate in space, so we're going to fix radial, fix axial, but allow tangential to rotate. We'll click OK. Next, we're going to come here, and we're going to apply another structural constraint. And this time, we're going to choose frictionless. This frictionless constraint can be applied to a surface, and it will allow that surface to slide around in that plane. Very, very useful. In fact, we're going to go back to the clip and apply it later. We're going to go ahead and say OK. And the last thing that we're going to do is apply a load acting down on this surface. And this load might be 200 newtons. We'll say OK. Now, let's go ahead and generate a mesh. We'll see the default mesh, see if it's any good. It's okay. It could be a little bit tighter. Let's go to mesh settings. Come to absolute. So we'll use the relative size. And we'll come along here and bring the slider down to about half of what it was. And regenerate the mesh. Lovely. That's a bit better, I guess. A little bit tighter. Lovely, that's looking much better. Okay, so what we anticipate is that the load is going to act down on this surface. The lever is going to rotate about this pin, and this surface is going to slide either back or forth. We'll see. Let's go ahead and solve it. Now, again, we could solve it locally or on the cloud. Let's go ahead and solve it locally because, again, it's a small problem. One of the benefits of solving on the cloud is that the cloud's computational capacity is much greater than your local machines. So if you have a solution that might take a few hours to solve or a few days to solve, you could send it to the cloud and it could be solved in anywhere between minutes and hours. It's just solving, solving, solving. Lovely. Oops, still going. And there we go. Solved. Okay, so let's have a look at what we're looking at. What we've got is our lever. Now, we might want to say, oh, is it actually rotating about that pin? It kind of looks fixed. We can actually inspect it by animating the deformation. So what we'll do is come here to animate. And here, when we click play, we can see, oh, I might set it to go 2A and increase the speed. There we can see the lever rotating back and forth over the pin. Lovely. So I would say that that's an accurate representation of at least the stress in the material. It doesn't account for the stress going through the pin itself. Now, what is the maximum stress, the maximum displacement that's going through this pin? Let's have a look. So we're going to stop the animation. And we're going to change, we're going to have a look at stress here. Now, we can see that the maximum stress is 56.4 megapascals, which we can see concentrated around this fillet area. Now, I might have said, oh no, I've forgotten, what is the yield strength of aluminium 6061? In which case, I can find the material in the study materials here, and right-click and say Material Properties. And here we can see there's the Young's modulus, and here we've got the yield strength of 275 megapascals. From the legend, we can see that the maximum stress here is 56 megapascals, so well below the 275 megapascal yield limit. We can see that when we go over to safety factor, and we can see that the safety factor, the minimum safety factor is 4.8, so it's very well off, I think, both for fatigue and for yield. How much does it deform? So we'll come along here to displacement, and here we can see that the peak deformation is actually 0.2884 millimeters experienced at the tip there. Now, I'll show you a very fancy trick. What is the resultant force on this surface here? You might want to say, you could do a very quick hand calculation to work out what that resultant force is going to be, but you could also cheat and have the FEA tell you. So we can come over here to inspect, and here we can see reactions. Go ahead and click reactions, and click this surface here. And what we can see in this little window is a summary of the reaction force that's that was required to keep this thing as a static problem. So we can see that the static force is 329 newtons. Now, if you recall, the force down here was 200 newtons. You might ask, why is it different? Why is it 200 at this end and the reaction force is 330? That's because this is an uneven lever. This arm is longer than this arm, and therefore a smaller force applied over a longer distance will equate to a larger force over a shorter distance. So you could get a lot of leverage from such a design. Very, very simple. So that frictionless design, that frictionless constraint was very interesting. I'll show you what it's doing there. You won't be able to see it very much because it's deforming, moving very little. But if you look very closely, and if I adjust the deformation scale, you can see it sliding back and forward in that plane. Now, that arch from the previous exercise, it was doing pretty well, with both of those feet fixed. But what would happen if I had one of those feet not fixed? I'm going to adjust this fixed one. Now, what I could do is I could right-click, I could untick fix to suppress it. I could just say, get rid of that constraint there and replace it with frictionless constraint. But I'll show you something that's equally useful. I'm going to edit this fixed constraint. And by default, a fixed constraint will fix the degrees of freedom in X, Y, and Z. So what does this mean? If you look at the view cube, here you can see the axes that that denote X, Y, and Z. We can see the X direction allows that foot to slide in this direction, like that. Now, what I'm going to do is free the X, the degree of freedom X by unticking it there, and click OK. And we're going to run the solver again. Now, from memory, this had a safety factor of 2. That was because the arch is quite a strong shape. But what we're going to see is if this foot is allowed to slide out, it's going to break the arch, and we're going to experience quite a bit more stress. We'll let it calculate. Might need to feed my computer a little bit of coffee. Or maybe I should have done a cloud solve. We shall see. Solving. And there we go. Lovely. So let's have a look at what we're looking at this time. We're going to use our adjusted deformation scale. And here we can say, whoa, okay, it's sliding out sideways this time. Okay, so how much stress is it going under? Oh no, catastrophe. It's 249.4 megapascals of stress there. Now, I might have forgotten that it's 207 megapascal yield limit, so let's have a look at the safety factor. Oh no, this is terrible. The safety factor is now below 1, which means that the stress is exceeding the yield strength of the material, and we would see plastic deformation in the clip. What does that mean? It means that once the load is applied and removed, the shape won't return back to normal. Catastrophe. Okay, so let's move on to another one. We're going to have a look at a practical design problem. Here we have a cleat, and it's going to be held in an interesting way. We'll quickly have a look, and we'll see that the cleat is 4 millimeters thick, and it's going to be fixed with 2 pin joints that will connect here and here, and it's going to be loaded with 6,000 newtons acting down on this pinhole. It's also going to be prevented from wobbling from side to side with a frictionless constraint on the side. Whether that's realistic is very dependent on the problem, but we'll have a look at it anyway. Let's go over to design and go to simulation. Again, we'll choose static stress. Now, we'll start off by prescribing the material. This time we'll choose mild steel. We'll go down to steel-mild, and click OK. And next, what we're going to do is apply our structural loads. Now, what I'm going to do is put a pin constraint, but I'm going to free up the axial degree of freedom. So this pin isn't going to prevent movement axially. I'll click it there, and I'll do another one down here. Again, making sure that axial is freed up. Next, what I'm going to do is apply a frictionless constraint that will keep this surface from moving out of whack. It won't be able to move in the Z axis, that is to say, side to side. Okay, next what we're going to do is apply a load acting down on the surface. Now, I have to warn you, the temptation might be to come along here and just apply a load uniformly across the surface. But this is wrong, because if we were to just apply a load uniformly across that surface, it would equally distribute the 6,000 Newton load across the entire surface of that hole. Now that might be the case if you've got the rod in there and you've epoxied the inside, or you welded the inside. But if you've got a rod that's jammed in there and you're pulling down, the load will only be distributed across the lower face and in a sinusoidal distribution. So to capture that, what we're going to do is come here and say bearing load. There we go. And as you can see, the glyph has changed. And this time, as before, we can change the direction if we wanted to. We're just going to have it facing directly down with 6,000 newtons. Oops, not 60,000, 6,000 newtons. Lovely. And let's click OK. Okay, lastly, we'll go ahead, we'll mesh it up. Looking pretty good, wonderful. And we'll solve it. it's saying that there is a warning. It might be, we'll have a look. Not enough constraints to find in load case. It happens to be that there are, but I won't tell the machine that, and we'll solve it. And here we have the safety factor. So the safety factor, it's failed. It's gone beyond the safety factor of 1, so it's going to plastically deform. If we look at the stress, we can see that it's 353.5 megapascals in that whole area. So how could we rectify this? Well, the obvious thing is to make the cleat a bit thicker. It's only 4 millimeters wide, so let's go ahead and make it, say, 8 millimeters wide. We'll come to Finish Results, go back to our design environment, come to our extrusion, and here we can play around with the thickness of the cleat. So I might say, let's go ahead and change it to an 8 millimeter thickness. There we go. And we'll come back to our design environment, simulation, and wonderful, it's remembered all of our settings. These faces haven't changed, they've become a bit longer, but it remembered our load case. So there we've got our loads, and there we've got our constraints. Lovely. However, the geometry has changed, and so it's going to have to remesh. We can see that we've got a little warning next to mesh. It just says it's out of date, and all we need to do is right click and say generate mesh. Lovely. Okay, lastly, we're going to click solve, and we'll click solve, and we're going to see, and hopefully we'll get a safety factor of greater than 1, meaning that our cleat won't deform when loaded. Well, it will deform, but it won't deform plastically. Okay, so yay, wonderful. There we can see we've got a maximum stress of 179 megapascals, and it's centered mainly around there. Now, if you pay attention to where the stress is being concentrated, we can see that there's a large portion in there that's not concentrated. If we wanted to, we could probably get rid of a great bit of material if we wanted to lightweight this thing. Let's have a quick look at what that might look like. We'll come along to design, and let's go ahead and we're going to butcher this design by using project geometry and offsetting this to cut away some material there, say for example. Pretty rough stuff, but it should do for this exercise. We'll say extrude, and we'll extrude it all the way through. Lovely. And to get rid of any potential stress concentrators, we're going to add little fillets up there. Stress likes to concentrate where the direction of the material changes quickly. So there we go. Lovely. Now let's see if this really quick lightweighting has led it to be lighter or has led to disaster. Let's go ahead and solve it. Oh wait, we have to remesh. And then let's solve. Wonderful, excellent. We can see that we've gotten rid of the material on the inside. And while there is larger stress around here, we can see that still the maximum stress is 178 megapascals and centered around that hole. So it's looking pretty good. It looks like that lightweighting maneuver did succeed. Okay, I'm afraid that's all we have time for today. I hope you learned something. There's a lot more to learn when it comes to FEA. And we will cover that in future episodes. We might cover some things like buckling, contacts in assemblies, fatigue. Ooh, fatigue's a good one. But until that time, please stay safe, wash your hands, stay inside, please, and continue to learn during this time. We're all in this together. We're going to make it together. And thank you very much for paying attention. Until next time. Bye.